This video will cover model evaluation and overfitting. By the end of this video, you should understand how we evaluate the predictive power of forecast models, why in-sample loss is a poor measure of the predictive power of a model, and what the distinction is between a training and a test sample. Data scientists make many choices when developing predictive models. You'll choose a modeling tool. Frequently, you'll choose the features to include. Things like the powers and interactions of existing features are some choices you might make. You'll also need to make other decisions to tune some modeling tools. Because of all these choices, two independent data scientists may develop completely different models, even if given the exact same data. As an example, suppose you're interested in forecasting electricity demand. You want to make sure you find the best model, so you hire several data scientists. You provide each of them with identical data on electricity consumption, and then determinants of electricity demand, things like weather, special events, and any other determinants you can think of. You tell them you want to use mean square error as your loss function, but leave all of the other choices up to them. You ask for a predictive model, some reproducible R code, and a 3-page memo describing the process they went through to construct the model. After you receive their submissions and compare them, you find out all of the models make different predictions. Reading through their memos, you realize they all use different modeling tools or use different features in their models. But how can you tell which model is better? You're frequently going to be presented with situations where you have to compare many models against each other. This process of comparing and assessing the quality of their predictions is called model evaluation. So how could we evaluate and compare these models? If only there was some way that we could condense all of the prediction errors from these models into a single number, then we can compare each model and choose which one is best based just on that number. But this is exactly what the loss function does. So how could you evaluate these models using the loss function? You could use each model to make predictions on the data you provided. You could then compute the value of the loss function for each model, and you could use the model with the lowest value of the loss function. But is there anything that could go wrong with this approach? In fact, this is not the way we evaluate models against each other, and I'll explain why through an example. So suppose you're in a class with pop quizzes, and you want to predict when the quizzes will happen. What this means is you want a model that forecasts when quizzes will happen. After 3 quizzes, you notice the professor of the class was always wearing a blue shirt in the class before each quiz. So you're going to predict there will always be a quiz after the professor wears a blue shirt. Based on the data that you have, this model has a mean square error of 0. But do you think it's a good model? You might worry that you don't have enough data. So suppose instead you've collected data from hundreds of this professor's classes. You build a much more sophisticated model in R to forecast the quizzes. You include all the data and then pick the model with the lowest mean square error. The model that you wind up choosing includes information such as the shirt color the professor wore in the class before, the day of the week, the current price of gold, the high temperature in Piscataway, New Jersey, the average flight delay out of Los Angeles International Airport, and pretty much every other variable you thought about adding. Do you think this is a good model? In both of these examples, we found models with very low mean squared error, a very low value of the loss function. But how can we tell if they're a good model? Each model seems to make really good predictions on the data that we have. But are they good models for predicting quizzes? I think it's important to reflect on why the mean square error in each of these models is so small. The modeling tool that we're using tries to find the model with the lowest mean square error. Every time we add a new feature, we can use it to lower the mean square error of a model. In fact, with any model, if you add features or other types of flexibility, that will always reduce the value of the loss function. This is going to make us think that models have more predictive power than they really do, and the effect is called overfitting. This is a very important issue in data science and machine learning. Overfitting is a huge challenge in modeling. Modeling tools are always going to minimize the loss function for predictions on their training sample. If you add new features to the model, you can't make the loss function any worse. In fact, it will always make it at least a little bit better. This is going to lead us to include irrelevant features in our models. So let's think about this for a minute. What do we want to do with these models? Do we just care about minimizing mean square error? No. The purpose of making these models was to just forecast quizzes. So how can we evaluate a quiz forecasting model? As a more concrete question, if your friend gave you a quiz forecasting model, how would you determine if it's any good or not? If it were me, I'd ask them to predict the next quiz and see if they were right. This is exactly how you should think about model evaluation. In the case of the quiz forecasting model, we'd like to look at how well it predicts future quizzes. So how could we implement this idea in general? Well, we could construct the model, then collect some new data, and see how good the predictions are. This approach is the gold standard in forecast evaluation. It's evaluation using out-of-sample fit. We call this measure out-of-sample fit because we're evaluating model predictions on different data than was used to train the model. The sample of data that we use to compute the model fit is called the test sample. and it's going to be distinct from the training sample. There'll be no information that overlaps between the test sample and the training sample. So why do we care so much about out-of-sample fit? It's because we're trying to make predictions. The best way to test a prediction is to see how close you get when you don't know the outcome ahead of time. And this is exactly what out-of-sample evaluation does. We're going to test predictions on data that wasn't used to train the model. So how can we go about selecting forecast models using out-of-sample fit? Well, what you could do is you could collect some data, use those data to train models, then you could wait for some new data to come in, and then use those models you trained before to create forecasts on the new data. You'll then compare forecasts to the actual values on the new data using that loss function, but only on that new out-of-sample data. Why does this process lead to better models? Models that are overfit will tend to create bad out-of-sample predictions. Choosing models with the best out-of-sample value of the loss function are going to select models that actually perform forecasts well. Usually though, you don't want to wait for more data to come in when you're choosing models. We want to make better decisions now, and that means we need to evaluate our models now. So how could we do out-of-sample fit analysis on our data right now? You can do this without waiting for new data. You can just divide your data into two parts. One part will be the training sample. It's a portion of your data used to train models. The second portion will be the test sample. It's a portion of your data used for evaluation. You're going to train models on the training sample, then you're going to use those models to evaluate predictions on the test sample. This is exactly the same as waiting for new data for your test sample, because data in the test sample wasn't used to train the models. It's only used for forecast evaluation. So how should you go about dividing data into training and test samples? Model predictions are more precise when you use more data to train them. But evaluating predictions are less sensitive to the number of observations that you use for evaluation. This means you'd rather have a large training sample and possibly a smaller test sample. And so what you'll do is allocate more data to your training sample than your test sample. Usually people allocate between 80 and 90% of the data to their training sample and the remainder to the test sample. There's no one correct number, and it really depends on how much data you have and the type of modeling tool you're using. The method you use to divide your data is also important. Generally, you're going to divide your data randomly. This way, your training and test sample are similar, but don't contain any overlapping observations. You should be aware that other methods of dividing your data might be appropriate depending on the nature of your data. For example, if there are really strong time trends in your data, you might want to randomly divide blocks of time instead of individual observations. R and the Tidyverse provide several methods for dividing your data into training and test samples, and we'll cover those in future videos.